Welcome. In this session, we'll explore problem number 775, global and local inversions. This is a fascinating problem that combines array manipulation and inversion counting. We'll discuss different approaches to solve it, analyze their complexities, and highlight the key insights needed to tackle similar problems. Let's dive in. In this problem, we are working with an integer array nums of length n, where nums is a permutation of all the integers from 0 to n1. The task involves two types of inversions, global and local. A global inversion is defined as a pair of indices, I, j, where I is less than j, and the value at nums, I, is greater than the value at nums, j. On the other hand, a local inversion is a stricter case where the indices are adjacent, specifically, I plus 1, and again, nums, I, is greater than nums, I plus 1. The goal is to determine whether the total number of global inversions is equal to the total number of local inversions. If they are equal, we return true, otherwise, we return false. The output of the problem is a Boolean value, either true or false. It is true if the total number of global inversions is exactly equal to the total number of local inversions, and false otherwise. Let's look at some examples to clarify this further. For the input nums equals 1, 0, 2, the output is true. Why? The global inversions in this case are 1, 0, meaning nums, 1, nums, 0. The local inversion is also 1, 0, as nums, 1, nums, 0, and the indices are adjacent. Since the total count of global and local inversions is the same, the output is true. Now, consider the input nums equals 1, 2, 0. Here, the output is false. This is because the global inversions are 2, 0, and 2, 1, where nums, 2, nums, 0, and nums, 2, nums, 1. However, there is only one local inversion, 2, 1, where nums, 2, nums, 1. Since the number of global inversions, which is 2, does not equal the number of local inversions, which is 1, the output is false. As another example, if the input is nums equals 0, 1, 2, 3, the output is true. In this case, the array is fully sorted, so there are no global or local inversions, resulting in both counts being 0. Since these counts match, the output is true. In addition to these examples, the problem comes with some constraints and edge cases to consider. The constraints specify that the array nums has a length n such that 1 equals n equals 10⁻5. Each value in nums is unique, lies within the range 0 to n1, and represents a valid permutation of the integers. For edge cases, when n equals 1, such as nums equals 0, there are no possible inversions, so the output is true. Similarly, if the permutation is completely sorted, like nums equals 0, 1, 2, and 1, there are no inversions of any type, and the output is also true. On the other hand, if the permutation is reversed, such as nums equals n1, 2, 1, 0, there are many global inversions, but not all of them are local, meaning the output will be false. Another important edge case is when n is very large, up to 10⁻5. In such cases, the solution must be efficient, ideally running in O(n) time. This is important because brute force approaches using nested loops to count global and local inversions would be too slow. The challenge lies in finding a way to determine whether the difference between global and local inversions can be resolved in a computationally efficient manner. To solve the problem of determining whether all global inversions in the array are also local inversions, we first consider a brute force approach. The idea here is to count global inversions by iterating through all pairs, I, j, where I less than j, and check if nums, I, nums, j. At the same time, we can count local inversions by examining adjacent elements, specifically checking if nums, I plus 1. Once both counts are obtained, we compare them to determine if the condition holds. However, this approach is computationally expensive. The nested loop required to count global inversions leads to a time complexity of O(n squared, which becomes infeasible for large arrays. Additionally, it has a space complexity of O(1), but the inefficiency in runtime makes it impractical for this problem. This inefficiency highlights the need for a more optimized solution. A critical observation provides the foundation for improving our approach. While every local inversion is inherently a global inversion, not all global inversions are local inversions. This insight forms the basis for a faster, more efficient method. The key to optimizing the solution lies in understanding the relationship between global and local inversions. For the condition that all global inversions are local to hold, there cannot be any global inversions arising from pairs I, j, where j greater than I plus 1. This means the array must be almost sorted, with each element being at most one position away from its original index. A crucial insight here is that for any valid permutation, we must ensure that no element nums I is greater than the maximum value seen so far in the array max nums 0 y1 by more than 1. This ensures that no invalid global inversions exist. Based on this observation, we can develop an efficient strategy using a single-pass linear scan. By keeping track of the maximum element encountered so far, we can verify the condition for each element in constant time. This approach eliminates the need for nested loops and makes the solution highly efficient. The optimized approach has a time complexity of O(n), as we traverse the array just once, and a space complexity of O(1), since no additional data structures are required. The implementation of this strategy in Python is straightforward. We initialize a variable max_scene to keep track of the maximum value encountered so far, starting with the smallest possible value. As we iterate through the array, for each index I, we calculate the maximum of max_scene and nums I. We then check if nums I plus 2, the next element after the local inversion window, violates the condition by being smaller than max_scene. If this condition is met, we immediately return false, indicating that the array contains invalid inversions. If the loop completes without any violations, we return true, confirming that all global inversions are also local inversions. This simple yet powerful approach efficiently checks the required condition without explicitly counting inversions. When comparing the two approaches, the brute force method stands out for its simplicity but is impractical for large inputs due to its O(n²) time complexity. It may be useful for testing or very small arrays, but its inefficiency makes it unsuitable for real-world scenarios. The optimized approach, on the other hand, is highly efficient with a linear time complexity of O(n) and constant space complexity of O(1). By leveraging key mathematical properties of permutations and utilizing a single-pass linear scan, it avoids the overhead of nested loops and explicit inversion counting. This method aligns directly with the problem constraints and ensures scalability, making it the preferred solution. Ultimately, the optimized approach was chosen because it provides a clear, elegant, and computationally efficient way to tackle the problem, addressing both correctness and performance requirements. In this problem, we're working with a permutation of integers and analyzing two types of inversions, global and local inversions. A global inversion occurs when a pair of indices, I and j, satisfies I less than j and a, j. On the other hand, a local inversion is a specific type of global inversion where j is exactly I plus 1. Our task is to determine if the total number of global inversions is equal to the total number of local inversions. To start, we can use a brute force approach. First, we define the inversions. Global inversions involve all pairs I, j, where I less than j and a, j, while local inversions are limited to consecutive elements. Next, we iterate through all possible pairs in the array using nested loops. The outer loop iterates over index I, and the inner loop checks all indices j that come after I. For every pair where the condition j is true, we increment the global inversion count. This process gives us a complete count of all global inversions in the array. Now, to count local inversions, we simplify our iteration. Instead of checking all pairs, we only look at consecutive elements. Using a single loop, we iterate over index I from 0 to n2. For each pair of consecutive elements, if I plus 1, we increment the local inversion count. Once we have both counts, global and local inversions, we simply compare them. If the two counts are equal, the condition is satisfied, and we return true. Otherwise, we return false. While this brute force method is straightforward, it becomes inefficient for larger arrays due to its time complexity. This is where the optimized approach comes into play. The key insight for optimization is that for global inversions to equal local inversions, all global inversions must be local. This condition can only be satisfied if no element I is greater than I plus 2, or any element beyond. Using this insight, we can iterate through the array efficiently. During this iteration, if we find any element I that violates this condition, we return false immediately. If no violations are found, we return true. This dramatically reduces the computational effort. The brute force approach, while conceptually simple, is computationally expensive. Its nested loops result in an n² time complexity, which becomes impractical for large arrays. For example, if n is 10,000, the number of operations grows quadratically. This inefficiency is why we turn to the optimized approach. By simply ensuring that no element I exceeds I plus 2, we eliminate the need to explicitly count and compare inversions. This direct check guarantees that all global inversions are local inversions, providing the desired result in linear time. Additionally, there are several edge cases to consider. For instance, a single element array or an array with just two elements always satisfies the condition, as there are no opportunities for non-local inversions. Similarly, a sorted array in ascending order meets the criteria trivially, while a descending order array always fails. The data structure used for this problem is straightforward: a single array. All operations, whether brute force or optimized, are performed directly on the input array. In the brute force approach, we may use two counters to separately track the counts of global and local inversions. When analyzing time complexity, the brute force method involves n² operations for counting global inversions due to the nested loops, and an additional n for counting local inversions, leading to an overall complexity of n². In contrast, the optimized approach requires just a single pass through the array, resulting in a linear time complexity of n. This makes the optimized method significantly more efficient, especially for larger inputs. In terms of space complexity, both approaches are highly efficient, requiring additional space. This is because all calculations are performed in place without the need for extra data structures. Let's look at an example to understand the brute force method. Consider the input array 1, 2, 0. For global inversions, we examine all pairs I, j, or I less than j. The pairs 0, 2, and 1, 2 both satisfy the condition I, j, giving a total of two global inversions. For local inversions, we only check consecutive pairs. Here, only the pair 1, 2 meets the condition, resulting in one local inversion. Since the counts of global and local inversions are not equal, we return false. Using the optimized approach for the same input, we check if any I is greater than I plus 2. Here, A0 is 1 and A2 is 0. Since 1 greater than 0, this violates the condition, so we return false immediately. Now consider another input array 1, 0, 2. Again, we check if any I exceeds I plus 2. In this case, no such violations exist, as the array satisfies the condition for all valid indices. Therefore, we return true. This example highlights how the optimized method efficiently determines the result by directly checking for violations, rather than explicitly counting inversions. This solution efficiently determines if the number of global inversions equals the number of local inversions. The key observation is that for the condition to hold, no number should be further than one position away from its original index in a sorted array. This is because any global inversion that isn't a local inversion would require such a mismatch. The algorithm iterates through the array, comparing the absolute difference between the value of the element and its index. If this difference exceeds 1 for any element, the function immediately returns false, as it indicates a global inversion that is not local. If the loop completes without finding such a mismatch, the function returns true. The time complexity of this solution is n, as it involves a single pass through the array, and the space complexity is 1, as no additional data structures are used. This is the Java implementation of the LeetCode problem number 775, global and local inversions. The logic mirrors the Python solution, where the key idea is to iterate through the array and ensure that no element is more than one position away from its original index. The implementation uses Java-specific syntax, such as the math.abs method for absolute difference and type declarations for the input array. The solution is efficient with an n time complexity and constant space usage. In this problem, we're tasked with determining whether the number of global inversions in an array is equal to the number of local inversions. A global inversion is any pair of indices I and j such that I less than j in nums I, nums j. A local inversion, on the other hand, is a specific type of global inversion where j equals I plus 1. The key insight here is that for the condition to hold true, no element in the array can be more than one position away from its original index in a sorted array. Let's look at an example. If the input array is nums equals 0, 1, 2, the global inversions and local inversions are straightforward to identify. Since the array is already sorted, there are no inversions of either type, so the numbers match. This means the condition is satisfied, and we would return true for this case. Now, let's break this down step by step for the array nums equals 0, 1, 2. We iterate through each element of the array and check if the absolute difference between the element's value and its index is greater than 1. At index I equals 0, the value is nums 0 equals 0. The absolute difference abs nums 0, 0 is 0, which satisfies the condition. Next, at index I equals 1, the value is nums 1 equals 1. The absolute difference abs nums 1, 1 is also 0, so the condition holds. Finally, at index I equals 2, the value is nums 2 equals 2. The absolute difference abs nums 2, 2 is again 0, satisfying the condition. Since no element violates the rule, the array meets the criteria, and we return true. Let's consider another example with the array nums equals 1, 0, 2. First, we check the condition for each element. At index I equals 0, the value is nums 0 equals 1. The absolute difference abs nums 0, 0 is 1, which satisfies the condition. At index I equals 1, the value is nums 1 equals 0. The absolute difference abs nums 1, 1 is also 1, so the condition holds here as well. At index I equals 2, the value is nums 2 equals 2. The absolute difference abs nums 2, 2 is 0, which satisfies the condition. Since all elements meet the criteria, there are no mismatches between global and local inversions, so we return true in this case. Finally, let's analyze the array nums equals 1, 2, 0. For the first element at index I equals 0, the value is nums 0 equals 1. The absolute difference abs nums 0, 0 is 1, which satisfies the condition. For the second element at index I equals 1, the value is nums 1 equals 2. The absolute difference abs nums 1, 1 is 1, so the condition is still satisfied. However, for the third element at index I equals 2, the value is nums 2 equals 0. The absolute difference abs nums 2, 2 is 2, which violates the condition because it is greater than 1. This means there is a mismatch between the number of global and local inversions, so we return false for this array. The key takeaway is that if any element is more than one position away from its original index in a sorted array, the condition will fail. The algorithm operates in O(n) time since it checks each element once, and it uses O(1) space as no additional data structures are required. The time complexity of this solution comes from iterating through the array nums, which has a size of n. The algorithm uses a single for loop to traverse the array, and during each iteration, it performs operations that take constant time. For example, the expression abs nums I calculates the absolute difference between the value at index I and the index itself. This involves basic arithmetic operations like subtraction and taking the absolute value, both of which are O(1). Additionally, the if condition and the potential return false are constant time operations as well. Since each iteration of the loop is O(1) and the loop runs n times, the overall time complexity of the algorithm is O(n). This is derived from multiplying the number of iterations, O(n), by the constant time per iteration, O(1). Now, let's analyze space complexity. The algorithm is highly space efficient because it uses only a constant amount of extra memory, regardless of the size of the input array nums. The loop uses an iterator variable I, which takes up O(1) space. Importantly, no additional data structures are created, and there are no recursive calls that would increase memory usage. As a result, the space complexity is O(1) or constant space. When considering the best, average, and worst case scenarios, the time complexity remains O(n) in all cases. In the best case, the condition abs, nums, I1 is never true, so the loop completes without any early termination, taking n time. For the average case, the algorithm might terminate early at some point when the condition is met, but this does not impact the asymptotic complexity, which remains n. The worst case, where the condition is false for all elements and the loop iterates through the entire array, also results in n time. To better understand the efficiency of the optimized solution, let's compare it to the naive approach. The brute force method involves explicitly counting all global and local inversions. For global inversions, you would need to check all pairs I, j, or I less than j in nums, I, nums, j, which requires nested loops and leads to a time complexity of n squared. Local inversions, on the other hand, only involve adjacent pairs I plus 1, where nums, I plus 1, requiring n time. After calculating both, you would then compare the results. This naive approach is inefficient because the nested loop for global inversions dominates the complexity, making it n squared. By contrast, the optimized solution eliminates the need to explicitly count inversions. Instead, it leverages the key insight that for the array to be an ideal permutation, all global inversions must also be local inversions. This simplifies the problem to checking the condition abs, nums, I equals 1 for all indices I. The optimized algorithm achieves a much more efficient n time complexity, representing a significant improvement over the naive n squared. Finally, let's solidify the time complexity analysis with a mathematical proof. The input array has a size of n, and the algorithm performs n iterations through the for loop. Within each iteration, the operations are constant time, 1. Therefore, the total number of operations is proportional to n. Formally, this can be expressed as the number of iterations, n, multiplied by the time taken per iteration, 1, resulting in n. This confirms that the time complexity is linear, n. On the other hand, the space complexity is straightforward. The algorithm does not use any additional memory beyond a few variables, such as the loop iterator. Since no additional data structures are created and memory usage does not scale with the input size, the space complexity is constant, or 1. This completes the analysis, showing that the algorithm is both time and space efficient. When solving the global and local inversions problem, there are some common mistakes to be mindful of. First, it's easy to misunderstand the difference between global and local inversions. Remember, a global inversion refers to any pair of indices, I and j, where I less than j and a, j. In contrast, a local inversion is a much tighter condition where j equals I plus 1. This distinction is crucial because confusing the two can lead to incorrect results. Another mistake is assuming that only consecutive pairs matter. While local inversions are indeed a subset of global inversions, not all global inversions are local. This means you need to account for pairs beyond just those that are adjacent. Additionally, brute force implementations, where you iterate through all possible pairs, I, j, to count inversions, can seem straightforward but result in inefficient n squared complexity, which doesn't scale for larger inputs. Optimized solutions are necessary here. You should also be cautious about constraints and edge cases. For example, arrays of size 1 or already sorted arrays might behave differently than you expect. Lastly, errors in indexing, such as going out of bounds while iterating through pairs like I plus 1, are common. Ensuring your loop conditions are correct will save you from unexpected bugs. Now, from an interview perspective, there are specific insights and strategies to consider. A key insight here is the relationship between global and local inversions. If all global inversions are also local inversions, the array is nearly sorted, which is a structural property you can use to optimize your approach. Recognizing this can help you avoid unnecessary computations. For more advanced scenarios, techniques like divide and conquer or using data structures like Fenwick trees or segment trees can be incredibly useful. These are especially relevant for related problems involving inversion counts. It's also important to weigh trade-offs. While a brute force approach is often simpler to implement and understand, optimized methods like merge sort bring the time complexity down to n log n, though they require a deeper understanding of recursion and auxiliary space management. Finally, during interviews, communication is key. Always clarify assumptions about constraints and edge cases like the size of the array or allowable values before you start coding. This ensures you're solving the right problem and helps you avoid unnecessary surprises. There are also several related problems and approaches to keep in mind. The global and local inversions problem itself, number 775, is directly tied to the concepts we've discussed, but others like number 315, count of smaller numbers after self, or number 493, reverse pairs, explore inversion counting in different ways. For example, number 315 focuses on counting how many smaller numbers come after a given number in the array, while number 493 extends this to more complex pairs. Another related problem is number 327, count of range sum, which involves range-based computations but also relies on divide and conquer techniques. When it comes to solving these problems, you have multiple approaches at your disposal. Brute force, though inefficient with O(n)² complexity, is useful for validating results from optimized solutions. Merge sort is a powerful alternative for inversion counting, reducing the time complexity to O(n) log n by recursively splitting and merging subarrays while counting. For dynamic inversion counting, data structures like Fenwick trees or segment trees provide efficient updates and queries. Lastly, for some constrained variations, a greedy or sliding window approach may be the fastest option. Choosing the right method depends on the specific constraints and requirements of the problem at hand. That wraps up our discussion on problem number 775, global and local inversions. We explored the problem, broke it down, and identified efficient strategies to solve it. Remember to focus on the constraints and properties of the problem to craft optimized solutions. Thanks for watching, and be sure to check out other problems to sharpen your skills. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!